So, a couple of days ago, during the last class, we just stopped, and when I introduced the so-called Lina-Wicher potential, which are a special case of the general solution of the Maxwell equations expressed in terms of the potential, so both the scalar and the vector potentials. In particular, this case, this interesting solution just concerns the very special case of just one single particle. So, as I was, the very last comments that I made last time was just about the way that the charge density function rho and the current density function J, what they look like in this very special case. So having to do with just one single charge, which is point-like charge, the charge density function is just delta function times Q, where Q is the electric charge of the particle, and J is just the density, the corresponding charge density times the velocity of the charge, which I called U. So having defined R0 as a function of time, as the position of the particle as a function of time, so U is inevitably the time derivative, so is R0 dot. Please, could you, any one of you remotely connected, please, could you mute yourself because I can hear some noise? Thank you. So we also defined beta just as the velocity in units of speed of light. So beta is just U over C, because it's going to be a handy quantity to have to deal with. So what we are going to do now is just to replace these very... please, could you mute yourself? I can still hear some noise, please. Make sure you are all muted. I'm the only person allowed to speak. What we are going to do now is just replace, as I was saying, this particularly expressions, this particularly formulae for both rho and J in the solutions, the formal solutions of the equation. In particular, let's start with phi. So the scalar potential. Just this is the very general solution that I already showed last time. So the goal here is just simply to replace, to use this very expression for rho. Paying attention that in rho, in the numerator within the integral has to be calculated as a retarded function. So in particular, retarded function, this is a reminder. It means that it is calculated the generic r prime and at a given time, which is t minus the light travel time. Well, the light travel time is the distance between the generic r prime and the r, so the position at which you want to evaluate the function phi, over c. So this guy here is t minus the light travel time between the 2 points in space. Okay, you see that's the distance over c. So the time it takes for light to travel from r prime to r, or the other way around, the same. Just like that. So again, this is very general. We still have to replace the value, the specific value in this case of just one single particle. But before doing that, we can use a mathematical trick in the sense that here in the previous formula, you see, we just have one integral in space, in just r prime. Here we added another integral using this trick. Instead of if you look here at this argument, instead of putting all this stuff, we just call this t prime, and then we add a delta function, t prime minus all this guy here. So, and then the integral in dt prime. So if you look at the integral in dt prime, you see that you have a delta t prime minus, so it means all this guy by replacing, instead of t prime, just this guy here, which is exactly what we had here. It's just a trick, but of course is okay, because you're just exploiting the properties of the delta function. This is going to be very, very useful in the following, because moving on, now you can swap integrals. Instead of doing first the integral in dt prime, you now work out the spatial integral, so d3 r prime. And in particular, we also replace, instead of rho, we use exactly the mathematical expression for rho. So we have q, which is a constant, so get outside, of course, and then delta r prime minus r0 prime. Look, here our rho is to be calculated at r prime at a given generic t prime. So, of course, this guy here, r becomes r prime, and here the dependence on time is the dependence on tie prime. So, apart from that, that's exactly the same. Just if you look for a moment, you will see that there's nothing really dodgy, nothing hard to see. But then, of course, let's work out the integral in space. You see, you just have to replace the denominator by, instead of r prime, just r0 t prime, which is the value r prime equal r0 at t prime is just the value for which the argument of the delta function is 0, which is exactly what you want. So by replacing, instead of r prime, r0 at t prime, so you get the denominator that becomes like that. This guy here becomes r0 at t prime. And here the same. So in the argument within this delta function, you have r minus, before you had r prime, now you have r minus r0 at t prime. So this trick, and now we are left just with an integral in dt prime. This is very convenient for the reason that you will see in a moment. In particular, okay, in this slide I just copied the very last equation we had in the previous slide, okay? Just copied. So now we conveniently define a new quantity, which we call capital R, as a function of t prime, which by definition is just r minus r0 at t prime. So you see, if you look at the here, inside here, you see that capital R is nothing but the distance to be traveled between the generic R and the position of the particle at t prime, at the generic t prime. So given that this guy shows up many times, it's convenient, we conveniently define just a new quantity, just like that. And analogously, we define its modulus as just of course, the modulus of the corresponding quantity. Now, having defined capital R, you see that you can more easily rewrite the integrand function as just like that. So you have capital R showing up, appearing both in the argument of the delta, the numerator, as well as in the denominator. So now you have an integral with a delta. So to work it out, you have to figure out for which values the argument of delta vanishes, just like that. You see that the argument of this delta is not trivial. So you have to, because why? Because t prime shows up in two different places. In particular, here you don't know exactly how capital R depends on t prime. So you cannot find the value, but you can impose a condition. You can find a condition which would determine t prime, the specific t value for t prime, which make the argument of the delta function vanish. In particular, we call this special value of time for t prime t ret, which of course, as you may understand, stands for retarded time. Why? Because if indeed t ret is the solution which make the argument of the delta function vanish, it means that, well, it means exactly that the capital R evaluated at t ret is exactly the light travel time times c, of course. So the path traveled by light in the time t minus t ret, this is the path, has to be equal to the distance between. So having also in mind, remembering what the way we defined the retarded time last time, this is exactly the case. So t ret, I say it again, t ret is the retarded time which makes, has this property. The path traveled by light between t ret and t is exactly, equals the distance between the generic point and the position of the particle at t ret, okay? And so we know by definition that when t prime equals t ret, if you look exactly, the argument of the delta function vanishes, which means, of course, a good thing in the calculation. But before doing that, you have to pay attention about the integral, the independent variable. The independent variable here of the integral is t prime. So we have to make sure that we make a change of the independent variables. In particular, I define a new quantity tau. I'm just following, just to let you know, I'm following the treatment by Rybik and Leitman. Here they use t second prime. I didn't want to use this because it would be too messy. So I just defined tau. It's a kind of change of variable, okay? I'm changing variable of the integral. So you see, this is not so straightforward. Why? Because t prime, again, comes into play through two different channels, here and here as well. And here you don't know exactly how. So moving to the differential quantities, d tau is just dt prime, of course. And, well, you have to derive with r with respect to time. So r dot t prime dt prime, just like that. Now the goal, what is the goal? The goal is to rearrange all this integral within as a function of the new temporal variable tau instead of, so we have to move from t prime to tau. So if you look here, you can collect dt prime. So just among bracket, you have 1 plus r dot over c. I keep explicitly showing the dependence of r as well as of r dot on t prime. So r prime is a function of r dot is a function of t prime, which we don't know. Because it's not only a function of the position of the particle, or better, or the way the position of the particle changes with time, but also on the distance between the position of the particle and the generic point at which you want to calculate the scalar potential. But so here we use another trick. We have here r dot, but r dot can also be expressed as a function of this guy here. If you derive with respect to time r squared, so the modular square of r, well, on one side r squared, you can see it as just r times r, so the modulus times itself. So of course this derivative is just twice r dot, but you can also say this guy as the vector r scalar itself. So if you look at that and you apply the rules for deriving vectors, you see that this is also twice vector r scalar its time derivative. So it means that if you look at these two terms here, this one here and this one here, you can express r dot as a function of, you just take this guy, 2 and 2 vanish. So r vector over its modulus scalar, I should have here minus this derivative. But this derivative, if you look at the way capital R was defined, you see that the derivative of vector r with respect to time is nothing but minus the velocity of the particle. So minus u, calculated at t prime. Okay, look at that. So you immediately see why instead of writing d vector r over dt, I just wrote minus u, calculated at the same time. But if you look at here we have a vector over its modulus. So by defining its corresponding unity vector, and we call this n, this can also be written as minus its corresponding unity vector calculated at t prime. So I keep stressing the fact that all these quantities are a function of t prime, scalar u. Now all this stuff can be, finally we have a mathematical expression for r dot, which is minus this scalar product. We can put it into here. And so d tau becomes 1, here among brackets, become 1 minus the scalar product. Look, I have r dot over c. So over c can be attached to this term. So u over c is just beta vector, of course. So here you are just, the term among brackets is just 1 minus the scalar product between the unity vector n and beta, just like that. Now you can also invert. You can express dt prime, which is our ultimate goal, to accomplish the change of variable for the integral. So dt prime, just take all this guy on the other side of the equation. So dt prime is just d tau over this guy here, just like that. So again, here I changed the slide, but I just copied what we were left before. So this was the integral that we aim to calculate, and this was the result of our change of variable. So we have both the relation between, which defines the new variable tau, as well as the relation we just calculated between the two differential quantities. So now if you replace, instead of dt prime, this guy here, well, having in mind, remembering that the argument of the delta function is exactly what we defined as tau, you have just delta tau, just like that. And then here in the denominator, I just left t prime, because you can think of t prime as a function of tau, but it's more convenient just from purely from the purely writing point of view. It's much handier just to let t prime show up instead of tau, but else it is implicitly a function of tau. Okay, so just like that. Now the integral is much easier, because you see that this integral is just the value of the integrand function calculated that for the corresponding value at which make the argument of the delta function vanish. So t0 has to vanish, but t0 vanishes as long as t prime is exactly t retarded. So all this guy, yes, which is exactly what I just said. So saying that we take the value of this function when tau equals 0 is equivalent to say, by taking, instead of t prime, t ret, because when t prime, look at here, when t prime is t ret, it means that exactly this here. But if this holds true, it means that tau is 0. You have to look exactly the same. So asking for tau equals 0 is equivalent to asking for t prime equal t ret. But this means that the result of this integral is just replace all what I said. So instead of t prime, it's just t ret. And given that all the terms appearing in the denominator are function of t prime, are all functions of t prime, you just have to replace systematically t ret. That's why I stressed, I explicitly wrote the dependence of each of these quantities as a function of t prime, because now you see you have to calculate each of these quantities at a given precise time, which is the retarded time. So using the notation I introduced last time, this is exactly equivalent. It means that the scalar potential is nothing but that very function, but evaluated at a specific time, which is the retarded time. So given a generic R, given a generic T, for each single generic R prime, you have to calculate the corresponding retarded time. But in particular, having to do with a single particle, you have to find the very specific retarded time for which the light travel time of the particle between the retarded time and the current time, t, equals the distance between the 2 points. I'll show you then later on a figure which should make things probably more clearer. Yes, which is exactly this. So just summarizing what we've come up with, essentially this is the solution of the retarded scalar potential in the very case of one single charged particle. So the scalar field produced, generated by just one single charged particle moving as this guy here. So all this quantity, and we derive this, just calculate at the retarded time. So if you carry out the same exercise in the case of this vector potential, because so far we just applied this, we just obtained this for the scalar. Well, the scalar potential is almost identical, except for the fact that you have a vector. Going back to the previous, okay, here, look at this solution. You see, it's essentially does the very same, except for rho, you have J. But in the case of the linear potential, J is rho, is in particular the delta function Q, except for an additional factor, which is vector U. So that's where the solution for the vector potential, where this beta comes from. It's just that. The rest is just the same. So I'm not gonna do obtain this for the vector potential because the proof is almost identical. So the more subtle passages are exactly the same. So that's why let me save time and just write. But of course, it's good exercise for you to carry out the same calculation just in the case for the vector potential. So again, I made this figure to allow us to have to grasp in a more intuitive way what in the case of one single particle, what is the meaning of calculating a given function at a retarded time. So retarded time in the case of one single particle, it means if you have one single particle, you can imagine, you can figure out, you can see the trajectory of this particle. So let's assume that this is indeed the trajectory of this particle. Let's assume that we want to calculate both potentials at this point here in space, which here is just the origin of a generic reference frame. So this is just the position at which, at this position, at the generic time t, I want to calculate the potentials, okay? Now, let's have a look where the particle is at time t. So at the very same time at which I want to calculate the potential. Well, the particle is here. R0 calculated at the same time is here. But I don't have to consider the position of the particle as well as the velocity that it would have, that has when it's here. So it would be a vector like that. I didn't draw it, but you know better than me that the velocity is always tangent to the trajectory, so it would be a vector like that. But here the recipe tells you, I don't care, I don't want the velocity, the position, and the position, so r, and the velocity beta at the time t, but another time, retarded time. So what am I supposed to, how am I supposed to calculate? Well, you have to supposedly you know exactly the position, so the trajectory and the position of the particle as a function of time. So you should have, once you know that, you have all the ingredients to calculate the solution of this equation. The solution of this equation is the retarded time. So among all the possible points along the trajectory, you want the very point for which this guy here, so the difference, the position of the particle, the position of the generic position at which you want to calculate, as measured from the point of view of the particle, capital R. You want this, you want the distance to match exactly the path that the light would travel between the two times, so between the current time t and the retarded time. So you want that, you ask for the distance to match exactly the path traveled by light in that very time interval. So let's suppose you know R as a function of time. So you find the solution t ret, and you find that t ret is some time previous to t. So when the particle at t time, the particle is here. At a previous t ret time, the particle was here. And its velocity as a function of, in units of speed of light, was this guy here. So the recipe tells you the potential that you have here at time t depends on the position of the particle at the retarded time. So when the particle was here, and you have to use also the velocity of the particle at the very same time, so b at the retarded time. So ideally, for any point in space, you have to calculate t retarded. You find the position of the particle, which indeed affects the potential now, because you essentially allowed light to travel in the meantime from the position of the particle at the retarded time and now, if t is now. And so you see that what comes into play and what comes into these formulae is just these two guys. So the position and the velocity of the particle at the retarded time. Okay, so I hope this is, at least from a formal point of view, this should be now less obscure. Let me say. So why is this relevant to our ultimate goal? Well, I remind you that our ultimate goal is to calculate the resulting electromagnetic fields, and in particular, we'll see the radiation coming out from an accelerating particle. So being interested in the result in terms of electromagnetic field of a moving single particle, of course, we have to go through linear Wigner potential, which is exactly the solution for the both scalar and vector potential for just one single particle. So that's the reason why these potentials are very important. That's the reason why we spent some time on to derive them. And we will be using them in the following. So moving on, let's see a strictly related concept to what we've just seen, the so-called velocity and radiation field. So ideally, now we have the solution for the linear Wigner potential for both vector potential A and scalar potential phi. So the next step, if you think that you want to calculate the electromagnetic fields, well, you remember very well how once you know A, once you know phi, you remember the formula that we've seen. I remind you, we are assuming the Lorentz gauge. So you know how to calculate B. B is the curl of A. So once you know A, you can move to B to calculate in B, as well as phi. Remind you, phi, the gradient of phi is E vector electric field. E is minus gradient of phi minus 1 over C time derivative of A. I'm not gonna prove you it. You have to just make a lot of calculations, but it's not conceptually difficult. I would like you to have to bear in mind the logical passage here we are making. So we just derived A and phi, so we have all the recipe now to calculate both electric and magnetic field. Okay, just think of what we've what we've seen in the previous class. I let you enjoy yourself the fact that you end up with this very unfriendly solutions. You have to battle away at some algebra, but there's nothing difficult. And you will see that you end up with these two expressions. In particular, you see that you have, let's focus on the electric field, but you'll see that then once you know the electric field, it's just a matter of calculating a vector product for the magnetic field. So let's just focus on the electric field. You see that you just have the sum of two terms. The first one is called velocity field, and the second one is called radiation field. Why is this? Well, first of all, let's focus on the dependence on whether there is some velocity or whether there is some acceleration. Let's focus on the first. So I'm looking at the velocity field. If you look at the numerator, you see that you have here, well, here the direction, the generic direction at which you are evaluated. You are evaluating, I remind you, n is the vector, unity vector from the particle position, the retarded time, and the point, the generic point in space at which you are evaluating, in this case, the electromagnetic field. Beta is the velocity of the particle. And then these are just scalar. These are scalar quantity. So here you see that this term just depends on the velocity in addition to the other terms. That's the reason why it is called velocity field. Unlike this, if you instead look at the radiation field, you see that in addition to the velocity, here you have beta dot. Well, beta is a velocity, so beta dot is an acceleration. So one of the main differences is that here you have the acceleration of the particle, which means automatically, if you look here you have a double vector product. But if beta dot is 0, you immediately see that all this term, all the radiation field term, automatically vanishes. So it means that the radiation field vanishes as long as the particle is moving with constant speed, with constant velocity, actually, I should say. So the second term here just shows up, doesn't vanish, is non-zero, only provided that the particle is accelerating. If the particle is not accelerating, you don't have the second term. The radiation field just vanishes. Very important. Unlike the velocity field, well, you see the velocity field, even for a constant velocity moving particle, the velocity field is not zero. The second very important difference is the dependence on distance. So let's have a look at R. If you pay attention, if you compare the two different dependencies, you see that the velocity field scales as 1 over r squared. While the radiation field, if you look, scales as just 1 over r. So the velocity field scales at progressively large distances, just becomes negligible more quickly. Why this is important? Well, this is important because if you think of the Poynting flux, we already saw that is something that tells us about the flux of energy propagating. You remember that the Poynting vector scales as the electric field squared. But electric field squared, it means that in this case, this guy here vanishes because you have r squared, r to minus 2, r squared, r to minus 4. So if you imagine to calculate the flux through a spherical surface with increasingly larger radius, Well, you know very well that the surface of a sphere scales as r squared. But if the Poynting flux scales as 1 over r fourth, well, the total flux scales as 1 over r squared. So it means that if you consider a sufficiently distant spherical surface, the overall flux calculated through the entire spherical sphere will be negligible at some point. If you play the same game with the radiation field, you see that the radiation field scales, the electric field scales as 1 over r. So it means that the corresponding Poynting flux scales as 1 over r squared. But it has the same scaling as the same reciprocal scalings as the spherical surface. The flux, the overall flux of a surface, of a spherical surface, is just the surface of the sphere times the energy flux. But if the surface of the sphere is proportional to r squared and the Poynting vector is proportional to 1 over r squared, it means that their product is constant. So it means that no matter how far you move, the flux associated with the electromagnetic field due to the radiation field doesn't vanish. That's why we call this radiation field, because as long as this field is not zero, it means that this is something which is carrying away energy, because the corresponding energy flux doesn't vanish at large distances. So these are the two main differences. In particular, the velocity field, as I wrote here, is kind of generalization of the Coulomb's law. And if you think of Coulomb's law, you immediately recover the dependence on distance of the electric field. Indeed, the electric field scales as 1 over r squared. That's exactly the case. Another important property, which here I don't prove, because I didn't have time, but it could be a useful exercise, is that, look, both terms have to be evaluated at a retarded time. But as a matter of fact, and if you look at the direction of the velocity field, is not just n. N is the direction from the position of the particle to the point in which there is some observer, someone who wants to measure the electromagnetic field. It's not n, it's n minus beta. But this guy has to be calculated at a retarded time. So the very special case of a particle moving with constant velocity, if one works out the direction of this vector at the retarded time in the special case of a particle moving with a constant velocity, it turns out that the direction of this vector is constantly pointing to the current position of the particle. So as if there were no delay. So when you want to calculate the velocity field of a particle moving with constant velocity at any time, the direction of the electric field of the electric field is exactly pointing along the direction from the position of the particle and the generic point, calculated at the very same time. So instantly, the electric field due to the velocity field is, as I said, this is a very special case. So for a case in which you have a particle which is not accelerating, a particle with constant velocity means that it's not accelerating, you have the velocity field is directed along the sight of line, the line of sight, I would say. So has the same direction as the vector from the position of the particle at that very same time and the generic point in space. This is not straightforward to see. You cannot see just unless you are tremendously smart, and it's not straightforward. But if you make calculations in this very special case, you will see that. Okay, and as I said, yes, this is something here. It's just says what I just said. So again, radiation field because if you work out the flux, the energy, total energy flux across a given spherical surface at whatever distance you want, you see that the associated the flux, the total amount of energy crossing per unit time the surface doesn't vanish, doesn't get negligible, because both the Poynting vector and the surface of a given sphere scale in the same way with distance. Okay, so this is very important. And you see, this is the novelty of the radiation field with respect to the velocity field. So you see that having to do with a particle which either accelerates or doesn't makes a huge difference in terms of the resulting electromagnetic field. When the particle doesn't accelerate, you just have the velocity field, which essentially doesn't carry away any energy, which instead is the case for the radiation field. So we start appreciating the equation between accelerating particle means radiating particle, because you have a net amount of energy which is being propagated outward as a function of time. And of course, because of conservation of energy, it means that the particle itself is losing energy. So an accelerating, I keep saying particle, but of course, it goes without saying that it's always a charged particle, okay? Electrically charged particle accelerating is losing energy, because the resulting electromagnetic field, as we derived from linear Wiefert's potentials, is indeed propagating energy. So particle is losing energy, which is not the case when the particle is not accelerating. So the radiation field is this guy here. From now on, we will focus just on the radiation field, because we just saw that the radiation field is exactly what is related to the energy dissipated by the particle in terms of electromagnetic field. So again, I just rewrote here just the radiation field. That's why I call E-rad, because I just neglected. I do not consider anymore the velocity field, even if, of course, I know that there is also that component in the most general solution of the electromagnetic field. And B-rad is nothing but N vector E-rad. Of course, both have to be calculated at the retarded time. That applies as well, as we cannot change that, of course. And mind that N, where N, again, I keep saying, is the vector between the position, the unity vector between the position of the particle at the retarded time and the position at which you want to calculate the electromagnetic field. So it's important to remember that the set of three, E rad, B rad, and N, they are a right-hand triad. Not only that, but if you look at the formula for the magnetic field, you see that, well, this is just perpendicular. How can you see that? Well, the fact that I didn't say that, but I say it now. The fact that E is perpendicular to N, well, you see just from here. N vector, so the result of N vector is something perpendicular to E. So to N, sorry. So all this guy is by just following this formula is all this guy here, which is E rad, is perpendicular to N. So this is a vector product between two perpendicular vectors. And again, the result is perpendicular to both. So that explains why this is a right-hand triad. And of course, the right-hand rule tells you immediately that why E and R just like that. Not only that, but also here, the fact that both electric and magnetic field have the same magnitude. Well, just follows from here. These are two perpendicular vectors, one of which is just a unity. So the magnitude of this guy is just the magnitude of this guy here. just like that, okay? Let's make an example to understand exactly how it works. Let's suppose we consider the electric field of a particle which is moving with constant velocity. At some point, the particle bounces back. We call here this point, the central point, is the point at which the charged particle bounces back. So the particle is, at the beginning, is moving from left to right here, constant velocity, up to the point when it is here, it bounces back. So, and then it moves again, back again with constant velocity, okay? So essentially, it's a constant velocity case, except for one instant in which, of course, bounces back. When it bounces back, it means that it undergoes a huge acceleration for a very short time interval. So let's figure out what the resulting electric field looks like. Well, if you think that about what I said on the velocity field, I said the property in the special case of a constant velocity is that the electric field is always pointing along the position of the particle at that very time, as if there were no retarded time, as if there were. So in particular, let's imagine to see the particle just a few seconds before the bounce. When the particle is just a few seconds before the bounce, is here. For example, in this black dot here. So if I want to show the field line, the electric field line at that very moment, you see, the electric field is just this. In this case here, is just direct. The direction of the electric field points along the line of where the particle is at that very time. So what happens? Well, let's put it this way. If the particle hadn't bounced, the particle after some time would be here. Should there, if there had no bounce, if no bounce had taken place, the particle after some time would be here. So if you consider the electric field far enough, you would consider the direction of the electric field here as pointing toward this point, which is this point here, which is the point where the particle would lie in the absence of bounces. If you consider the electric field far enough, the electric field far enough is not yet aware of the change that happened due to the bounce. So the electric field sufficiently far away doesn't know that there has been a bounce. So the field lines just point toward the position where the particle would lie should there have been no bounce at all. Instead, if you consider closer distances, and that's the field lines here without this circle, the information about the bounce has already come. So the field lines within this sphere have already adjusted, and they are now pointing to where the particle indeed lies, because again, after the bounce, the particle resumed a constant velocity motion. So it means that the information about the change of the behavior of the particle, so the information about the fact that for a short time interval there was an acceleration, is traveling, and is traveling at the speed of light. So given that the speed of light is a finite speed, it means that the information about the change travels at the speed of light. So it takes some time for the information to travel and to inform all points in space that there has been a change. So you see, and indeed, so there is a, if you pay attention, if you look at the field lines across this sphere, which is exactly at some point, what is the radius of the sphere? Well, it's the radius of the sphere is the speed of light times the time interval after the bounce, because that's the path traveled by the information about the bounce. So, and looking in particular at the electric field lines here on the boundary, you see that there is a huge discontinuity. It means that the electric field here is changing. So there is some radiation which is being carried forward by this sudden change of the electric field lines. And indeed, according to what we've seen, indeed, this makes sense, given that the particle underwent some huge acceleration for a short amount of time. So it means that during that short amount of time, the radiation field was not negligible, had to be zero for a short amount of time. So the particle has lost some amount of energy. Apart from that, if you neglect the time interval in which the particle was accelerating, you just have the velocity field. The velocity field doesn't carry any energy. So this is just a way to visualize exactly what happens when the particle undergoes a temporary acceleration, as seen through the radiation fields, in particular, through the electric field lines, in particular, to see how this change affects the electric field. So now let's move on and let's work out, having established that an accelerating particle loses energy, let's be more quantitative and let's evaluate what's the amount of energy per unit time, and we also see some information. Okay, yes. So let's consider particles which are not relativistic. In particular, let's call U as the velocity of a generic charged particle, okay? So beta is much less than 1. Let's work out again. Here I use two different colors to denote the two different fields. Let's work out the ratio between the magnitudes of the two fields. So having established that when you move sufficiently far away, the velocity field is negligible with respect to radiation field. So it means that there are some, at some distance, close enough, probably the velocity field takes over, and the other way around when you move far away enough. So if you just focus on the most relevant dependence. So in blue, I just denoted the radiation field. So you see that E rad scales proportionally to the charge Q and to the acceleration beta, so linearly with beta dot. So of course it's proportional to U dot. So the acceleration, the modulus of the acceleration over what? Well, here I put C square because one C is here and the other C is implicit in beta. Beta is much less than 1, so you can neglect this term. And of course, as 1 over r, as I already commented. Let's work the same for the velocity field. On the velocity field, if you see, you have proportional to charge. Here, in the numerator, you just have n, because beta is much less than 1. N is 1, in the magnitude of n is 1. And here in the denominator, you just have r squared. To minus 1, because here the velocity field is the denominator. So you see the Q dependence just vanishes, and you are left with r in the numerator and c squared in the denominator, just like that. Why is this interesting? Well, because if you think of the motion of the particle as something periodic or essentially approximately periodic, you know that if you think of U as a function of sine, cosine, omega t, where omega is the pulsation of the corresponding periodic motion, you know very well that when you time derive a function which is a periodic function of time, you gain an extra factor of omega. And you as many omega as many times you derive. So in particular, here we have u dot. So the derivative, time derivative of u. But if u scales as something sine or cosine omega t, it means that the derivative gains an extra factor of omega. Here I didn't consider 2 pi, I just put nu instead of omega, but they are proportional, of course. So I'm interested in just an order of magnitude evaluations. That's why I don't care about 2 pi, okay? I just want to calculate things by orders of magnitude. So I can approximate, instead of u dot, as u times nu, where nu is the typical frequency of its oscillation, given that u is a periodic function, or almost periodic. So almost means that there is some kind of dominant time scale. So having said that, well, if you have the source of radiation, which is oscillating with a given frequency, automatically the radiation produced has to do something with the same frequency. So it means that, well, here I simply replaced u dot with u nu. But nu, I can also consider nu as the frequency of the outcoming radiation, the radiation produced by those oscillations of the particles. So if you look, C over nu is just lambda. If by lambda I mean the corresponding wavelength of the radiation. I've got one u over c, which is beta, and nu over c, which is 1 over lambda. So I can rewrite this as r is the same, u over c is beta, nu over c is 1 over lambda. This is useful. Why? Because you see, now you have expressed the ratio between the two components, so the ratio of the radiation field over the velocity field, as apart from beta, as the ratio between two lengths. In particular, r is the distance at which you are evaluating the two fields, and lambda is the wavelength of the radiation. And in particular, so this gives us a scale. If you evaluate the resulting electromagnetic field at a distance from the system of particles, which is much smaller than the wavelength of the radiation that you are considering, in that regime, it's the velocity field which is dominant, which is the dominant term. So when you are close enough, and we somehow expected this, but now we see in a more quantitative way, because close, far doesn't mean really much. How close? Well, at a distance which has to be much smaller with respect to the wavelength of the radiation. So when you are that close, you can neglect the radiation field with respect to the velocity field. The other way around, when you are in the opposite situation. So where you are at a distance which is not only much greater than the wavelength itself, but much greater than the ratio between the wavelength and beta. I remind you that beta is a number which is much smaller than 1. So, for example, could be 10 to minus 2, 10 to minus 3. So when this is a situation, when you are far enough, and this tells you how enough, what enough means. Okay, you are in the opposite situations in which I was already commenting when I first compared the two fields, in which it's the radiation field which is dominant, and which is what we are interested in. So finally, let's get to the probably most important result of today's class, which is Lamar's formula. In particular, what we derive is the power emitted by the source, by the single particle, both total power, but also we'll see as a function of direction. So to do that, we consider a non-relativistic limit. So the particle that we have in mind is non-relativistic. So again, using the same notation means beta is much smaller than 1. This is important to bear in mind, because we will see when we will generalize Lamar's formula in the relativistic case, things are changed significantly. So in this case, if you get back, let's consider the radiation field. You see, when beta is negligible with respect to 1, it means that here you just, instead of n minus beta, you can just write n. And also here, instead of this term among brackets, you just have 1, because beta scalar n is negligible with respect to 1. So the expression for the radiation field simplifies significantly. And so how much? Well, this is what you come up with. So as I said, the denominator is just 1 over r. You don't have 1 minus beta scalar n. And here, instead of n minus beta, you just have n. Okay? Relatively simple. So once you know the electric field, of course, it's just for kids to calculating the corresponding magnetic field. It's just an exercise for kids. So let's focus on the electric field. To figure out exactly, to calculate these vector products, we have to make a figure in which we see all these vectors. So let's suppose the particle at some point is here, lies exactly here where I draw, I've drawn the acceleration of the particle. So the particle, when it is here, is accelerating. This is u dot vector. But beware of that. I didn't write the arrow, but I just used the bold notation to mean vectors. So this is the acceleration. So the particle, we don't know where it is moving, but we know where it is accelerating. So it is accelerating upwards in this figure here. We observer are here. Observer, because we are interested in measuring the electromagnetic field here, at this point here. So n, if you remember, the way we define n is nothing but the unity vector telling you the direction from the particle to the generic point where you are when you want to evaluate the electromagnetic field. Now let's have a look. What's the direction for the electric field? Well, you have to calculate n vector u. So right-hand rule, n vector u, you have a vector coming toward you, perpendicular to the plane of this figure, and then you have to calculate again n times vector this guy. You see that the electric field is just lies on the plane, on this plane of the slide, and just directed this way. I invite you to work out yourself to apply twice the right-hand rules for the vector product. So indeed, just from here, you immediately see that E rad is this. But if you remember, and then of course B rad is n vector E. So B rad is a vector which is perpendicular to this plane, entering in, not out. Okay, so that's why I put here the corresponding symbol of a circle with a cross. No, now we know, and if you think, and immediately you can calculate, having already known that both electric magnetic field have the same magnitude, you can calculate the magnitude of this guy. Well, here, if we call with theta the angle between the acceleration and the direction n, so the modulus of this guy here, you just gain a factor of sine theta, the modulus of a vector product. And of course, this has modulus 1, and this is modulus just u dot. So u dot sine theta, and then the same. And then, of course, you have another vector product, this guy, vector this, but these two are perpendicular. So just the modulus of this guy, which we already calculated, and this is just 1. So this is the modulus, the magnitude of vector E rad, which is also the magnitude of vector B rad. Just like that, you see. Proportional to acceleration, you see. proportional to the magnitude of the acceleration, to the charge, over rc squared and sine theta. Now, you want to calculate the flux associated, because that's what we care of. But you have to go through Poynting's vector. And I remind you, here I want to calculate, I already know the direction of the Poynting vector. You see, again, the Poynting vector is E vector B. E vector B, you see immediately that S Poynting vector is pointing exactly, is parallel to N. And indeed, if you are there and you are looking at the particle, the radiation is moving towards you, observer, at any point. So this is just to make sure that things make sense. So let's, now that we know the direction of the Poynting vector, so the Poynting vector is parallel to N, let's work out its modulus. So here I put just the modulus. But you see, E and B are two perpendicular vectors. So again, their vector product is just the magnitude of this vector product is just the product of the two magnitudes. But the two vectors have the same magnitude. So the result is C over 4 pi and this guy squared. Just like that. You see, just as I wrote here, just because the two guys are perpendicular, electric and magnetic field are perpendicular with one another, with respect to one another, and have the same magnitude. But replacing the value of the magnitude for the electric field, you see that you have C over 4 pi at the definition of the Poynting's vector, and all this guy squared. So this is the Poynting vector. So I remind you, Poynting vector means energy per unit surface per unit time. We can think of, well, here I also, to mean power, I use the notation dW over dt, because W in English, of course, is work. So it's just the amount of work per unit time. So this is energy per unit surface per unit time. So it means that if you imagine to consider a surface element dA here perpendicular to N, it means that S Poynting vector times dA, this is a power, and this is exactly the amount of energy crossing dA, the surface dA, per unit time. But look, if you instead of considering a generic surface element dA, you consider the solid angle subtended by the surface from the point of view of the particle, well, it means that instead of dA, I can write, well, what is the solid angle subtended by a element surface dA here at a distance r from the source, from the particle? Well, r squared solid angle. So instead of dA, I can write r squared d omega. So d omega is the solid angle corresponding subtended by an elementary surface dA. But look, given that S is dW over dt dA, or equivalently dW over dt over this, it means that you can calculate the amount of energy emitted by the particle per unit time, per unit solid angle, just by multiplying. If you bring r squared and you put here, you see that just by multiplying the Poynting's vector times r squared, you just have this guy here. So taking the modulus of Poynting's vector and multiplying by r squared, it means that here the r squared in the denominator just vanishes, and you are left with this quantity, which no more depends on r. And indeed, this makes sense if you think of what we've just learned about the properties of the radiation field. The radiation field, it means that if you consider a fixed solid angle, it means that the amount of energy carried away within that solid angle by the radiation field cannot depend on distance. And that's exactly what we find here. So, but what is interesting in this formula here is that we found how much energy the particle is emitting per unit time and per unit solid angle. So there's a lot of information here on the right-hand side of this equation. In particular, we see how it depends, how it scales with charge, with acceleration, but also with direction, you see? It's not isotropic. The particle doesn't emit the same amount of energy to all directions. No, there's a sine square dependence. This makes a big difference. So moving on to the next slide, here I just copied the result of the previous formula. So for example, we can, if we don't care about the direction at which, about how much energy is emitted at different directions, we want just the total budget. So how much energy is lost per unit time by the particle? So what's the total power? That means just carry out an integral over the solid angle. So you integrate the result we have just obtained, integrating over the entire sky. So we just replace this. Mind that there is a dependence on direction, which is what I was telling you before. So there is a sine square dependence. So this guy cannot be just taken out of the integral, of course. In particular, let's work out this once. We will meet this guy many times, the integral over the entire sky of sine square of an angle with respect to a fixed direction. Here the fixed direction is given by u, okay? So you imagine to integrate across all the sky. So let's work it out. There is, of course, you have the integral in d phi, the azimuthal angle, and the polar angle, which is this guy here. So by integrating in d phi, you gain immediately a 2 pi factor, because there is no phi dependence. So the integral, you see, 2 pi just simplifies with 4 pi in the denominator. You are left with just 2 in the denominator. And then you have the integral on the polar angle. Mind that the solid angle element has in itself one sine theta. So sine theta times sine square, you have sine cube theta. And the polar angle goes from 0 to 2 pi. So the time boundaries in d theta is 0, from 0 to pi. From 0 to pi, not to pi. And so I just worked it out very, very simple way. So you can express sine cube as sine times 1 minus cos square. And so you can split the integral in 2 integrals. Well, this guy here is just minus cosine calculated between pi and 0, which is 2. And the second term is the integral is just 1/3 cos cube, if you look. 1/3 cos cube calculated between pi and 0 is minus 2/3. So this guy here gives you 2. This guy here gives you minus 2/3. So this guy here is 4/3. 4/3 time over 2 is 2/3. And this is the very famous Larmor's formula in the non-relativistic regime, because that's the regime in which we've been considering. So you are supposed to know this at any time of your life from now on. At any time, if someone just wakes you up suddenly in the middle of the night and asks you Larmor's formula, you have to know that. So it's easy to remember, at least easier in the Gaussian system. 2/3 and then q squared over c cubed, and probably the most important dependence, which is on acceleration, modulus squared acceleration. So if you double the acceleration, the charged particle loses 4 times as much energy. I immediately foretell you the relativistic analog of the Larmor's formula, which is this guy here, which looks pretty scarier than the previous one. You have plenty of gamma factors. Here, gamma is the Lorentz factor of the particle when the particle is relativistic. So first of all, you immediately see that if you consider the relativistic Larmor formula, and you consider in the non-relativistic case, so where gamma is 1, you see that gamma is 1, and among brackets here you have just a perpendicular plus a parallel, which is just modulo square of the acceleration. So you gain again this. I didn't say what are a perpendicular and what parallel are. What are they? Well, perpendicular and parallel to what? With respect to what? The answer is with respect to velocity. So you see that it makes a difference on whether the particle is accelerating with a fixed direction, so in which case A would be just simply A parallel. It costs much more because there's a gamma to the 6 power dependence. If instead the particle is as an acceleration which is entirely perpendicular to the velocity, for example, you might think of a uniform circular motion. That's a special case in which the acceleration is constantly perpendicular to the velocity, in which case you just have this one term here. And so the dependence on gamma is a little bit smaller, but still there's a huge dependence on the Lorentz factor. The question is, am I going to prove this? I let you guess the answer. We have all the ingredients to be able to prove, of course, and it's just a matter of a simple trick. So getting back to the point I was making, let's summarize the main results we obtain. Essentially two results. The total power emitted by the particle, which is exactly Larmor's formula here, and the power emitted by the particle per unit solid angle. As I stressed here, the emission is not isotropic, but there is a sine square dependence. So let's display. We want to see this. So let's assume that the particle at some point is accelerating in this direction. So again, we went back to the non-relativistic case, okay? So this is important to point out. Non-relativistic case. The particle at some point is accelerating in this direction. So as we defined theta as the angle between the direction of acceleration of the particle and the generic direction, you see that sine square theta, it means that if you are looking at the particle right on the direction here, if you are an observer right above here, you don't receive any radiation at all, because in that case theta is 0. So it means that if there is a charged particle moving towards you or exactly away from you, you're not going to receive any radiation at all. The best, or better, the position, the direction at which you will receive most of the radiation is the direction which is perpendicular to the, because when it is perpendicular, theta is 90 degrees. And so you see, there is a cylindrical pattern. It's kind of donut shaped. It's kind of donut. You saw the donut with a torus. It's kind of torus. So this figure here shows you the intensity of the radiation as a function of theta. So this is maximum when theta is 90 degrees is 0. So you see that this line has a distance 0, has a modulus 0 when you consider theta 0. So this is the pattern sine squared. And of course, it just depends on the polar angle. There is no azimuthal dependence. So there is a, okay. This is very important. So for example, if I consider an antenna you can think of just a bar, single bar, metal bar in which electrons are keep accelerating back and forth. So the acceleration of electrons is directed this way, parallel or anti-parallel to the bar. It means that if you look, if your receiver, you put your receiver parallel to the bar, you're not going to receive anything. The best way you will catch most of the radiation when you look at the antenna in a perpendicular direction. Now you should realize why antennas sometimes are displayed in such a way and are made in such a way. Let's stress, let's highlight the different dependencies on the different quantities of the power emitted by the particle. First of all, the scaling with the charge and with acceleration. So it's proportional to the charge squared. So instead of, if you take a particle which has twice as much charge, the power increases by a factor of 4. The same, the very same works for the acceleration. And this works both for the power as a function of direction and the total power. If you consider the pattern with direction, as we've just seen, so there is a sine square pattern, where sine square of the angle between the direction of acceleration and the generic direction. A third important point is that if you think of the way we calculated, we derived in particular the direction of the electric field. So if you get back to the figure that I showed you, well, I can do it straight away. So sorry for, here we go. Okay, so if you look at this drawing, if u is constant, if u dot is constant with time, so it means in the very case of a constant acceleration, it means that the direction of the electric field is constant as well for a given observer. But constant in direction, I mean. So you see an electric field which is oscillating within a fixed direction, and this direction doesn't change. But this means that the polarization of the radiation that you measure is maximum, because you have an electric field whose direction is fixed in time. So you have linear polarization, which has the highest degree possible, so 100% linearly polarized radiation, because the direction due to A, acceleration, and N doesn't change. So as a consequence, the direction of the electric field doesn't change consequently. It doesn't change either. This is something important to bear in mind. So moving on, dipole approximation. What is that? Well, so far we consider the case of one single particle. Now we try to kind of generalize things, sort of generalizing things by considering, we wonder what's the radiation due to a system of charged particles just moving within a given system. So to figure out exactly what are the most important aspects that become relevant, let's call by L, capital L, the size of this system. These particles are somehow bound to a system, to move within a system, and this system has a typical size that we call capital L. We also define a typical time scale over which particles change significantly their position within this set. Of course, if you consider a too short time interval, particles haven't moved enough. So there will be a typical time scale above, beyond which the configuration of the system might have changed significantly. We call it tau. Well, in the case, let's consider the case in which this tau is much longer than the light travel time of the system. What is the light travel time? Well, it is the time it takes for light to cross the system. So it's just L over C. So in other terms, let's consider the case in which the typical time scale we have to wait for a significant change in the configuration of the system is much longer than the light travel time. Well, given that the particle motions are bound to stay within the system, you can think of quasi-periodic motion of each single particle. And so the typical time over which the system can change is of the order of 1 over nu, where nu is the typical frequency of the motions which describe the particle. So instead of tau, I can put 1 over nu, where nu is the typical frequency with which particle just get back to a similar position. But for this reason I already told you before, I can associate nu with also the frequency of the outcoming radiation due to the particles themselves. So by calling lambda the corresponding wavelength is just nothing but c over nu. But if 1 over nu is much larger than L over C, it means that lambda, which is C over nu, is much larger than L. So considering this, considering a system whose typical time scale is much longer than the light travel time of the system, is equivalent, has as a consequence that the wavelength of the outcoming radiation is much greater than the system size L. An equivalent way to look at this is to consider the typical time scales as the time it takes for a particle to travel across its orbit. If we think of the motion of a single particle as kind of orbit. So let's call small l, lowercase l, as the size of the typical orbit of a single particle within the system. So time, tau, so a particle would get back to its position in a time scale which is the size of its orbit over its velocity, so L over u. But tau, we already demanded that tau has to be much greater than L over C. So the condition we saw above is equivalent to asking that L over u has to be much greater than capital L over C. But if you rearrange terms so as to express, for example, you put u this side here, so you have u over C, which is beta, and a capital L goes on the other side here. So it is equivalent to asking that beta is much smaller than the ratio of the orbit of the single particle over the system size. So in the same condition, it's equivalent to asking that we have to deal with non-relativistic particles. So when we deal, as long as we deal with non-relativistic particles, we are confident, we saw that having to do with a system of bound non-relativistic particles, the outcoming radiation will have a wavelength which is much longer than the size of the system itself. That's exactly what we obtain. Why is this relevant? That's explained in the first here piece that I showed, but I didn't comment. I haven't commented yet. When the size of the system is negligible with respect to the wavelength, it means that when you have to calculate the retarded times for all the different particles, it means that the differences, the mutual differences between the retarded times of individual particle and a generic distance, generic point in space outside, well outside the system, the mutual differences are negligible because the difference in the path to be traveled from one particle to the other as a function of wavelength is a negligible fraction, you see? Given that the system size, so the difference in the path to be traveled for different particles cannot be greater than capital L. But if L is negligible with respect to lambda, it means that the differences in the different path that you have to consider when calculating the different retarded times is negligible with respect to in terms of lambda. So it means that essentially the radiation fields, there is no much difference in the phase due to the different paths of the particle to a generic point. So it means that when you are supposed to sum up all the radiation fields due to the individual particles, in principle, you know very well that this sum, you should evaluate each single term of this sum calculating its own retarded time. So it's a mess. You have to calculate, in principle, the retarded time for each individual particle. But because of the regime that we consider, since the different paths, due to the different particles, are negligible with respect to the lambda, you can assume just one single position for the particles and calculate the corresponding retarded time as if they were all together at that point. So instead of calculating all the individual Ri, you just consider one single R0, some kind of center of the system. And so this is a remarkable simplification, because just one single retarded time. And in particular, given that we can calculate all these quantities at a unique time, you see that if you look at the term Qi here in the sum, Qi times, Qi is a scalar, so I can put it everywhere, times the acceleration of the IF particle, I see that I can sum up. All the other terms are constant. You see, are constant because they do no more depend on I. So there is no more a dependence on the individual retarded time. So I can, instead of considering Ni, I can consider just one single N. Instead of Ri, just one single R, which I call R0. So all these terms are constant. And the only thing which might depend on the individual particle is, of course, the individual acceleration and the individual charge. So I'm left with the sum of Qi times U dot I. But this is the second time derivative of a vector, which I called D, and which is defined, as you see here below, as the electric dipole moment. If you work out the second time derivative of D, you see that you have Ri double dot, which is exactly the acceleration of the IF particle. So you see that the sum just enters into this newly defined quantity, which is the electric dipole moment. It's a kind of weighted sum where the weight is given by the charge. Is a charge weighted summed position. You should have already encountered this quantity in your previous studies. And I put a couple of slides just as a general reminder of what I'm saying. In particular, if you remember the multipolar expansion that I'm sure you saw, for example, in terms of spherical harmonics in quantum mechanics, surely. For example, when you are supposed to Taylor expand, for example, the Coulomb potential of an amount of charges. So, for example, here in the continuous distribution, here I assume I want to calculate this potential, the Coulomb potential. At this point here, due to an amount of charge, here I have some charges distributed continuously over a given volume. So what the solution is just the integral of the charge density integrated over this volume, dv x prime means over this volume here. Well, you can develop this in, here I use the multipolar expansion in Cartesian coordinates. One can, I'm sure you did the same in spherical coordinates, and one ends up with Legendre polynomials and correspondingly also the spherical harmonics. Here I just used the scalar, the Cartesian coordinates. So if you develop just tailored expand, just like that, what? Well, the function here that you have 1 over, which is the distance, this guy here is the distance between a generic elementary charge in x prime and the generic point in space in which you want to calculate the potential. So you just Taylor expand this, you end up with the first 3 terms. I just stopped at the first 3 terms. So, of course, this is just the general first derivative, second derivative with all this stuff. I'm not going to comment too detailed because, and if one keeps on, you see that the first term, when you then replace this expansion, this Taylor expansion into the integral, you see that the very first term, which is just approximating as the distance from the center of the system, and here is just 1 over r. So Q over r is just the potential that you would have had, in which case, well, that's the roughest approximation. You just see one single charge, which is the total charge at the distance r. That's the first term, the dominant term, which, if one considers, is also the term in, is the only term in case of a total spherical symmetry. And this should connect with what you know about Gauss theorem, but this is another story. And indeed, Q is the total charge. The second term is, you can see it as a vector, a scalar product between two vectors, d and the generic r, where d is defined exactly as the dipole moment. Here, this is a scalar, this is a vector. You know, you see, this is a vector, this is a scalar, the total charge, this is a vector. Vector y, because j is just the Cartesian component of this vector, j, 1, 2, 3, or x, y, z, if you want. And if you look at this is, okay, I'll make a comment later on. So this is the second term, which you see, the total charge, the dominant term scales as 1 over r. The dipole moment scales as 1 over r cubed. So the third term is a two-rank tensor. So you remember that the vector can be considered as a one-rank tensor. Here we have a two-rank tensor, QJK, sorry, is defined as this guy here, as is the quadruple moment tensor. So that's why multipolar moment. Here I could make many comments. For example, the fact that so for example, if you compare this guy here, the dipole moment, this is the continuous case, but I also showed in the next slide is also about the discrete case, discrete in which the charges, instead of being distributed continuously over a volume, they are just a sum of discrete charges, point-like charges. But you see, okay, I did the very same, just considering the discrete case. So you see the dipole moment is just this guy here, which is exactly the Cartesian components, which is exactly the dipole moment that we defined when we were discussing the electric field for a system of charged particles. So that's the very same guy. And this is also interesting because if you, for example, think instead of having a charge distribution, you have a mass distribution. So for example, Q are just the individual mass particles. You see that this is reminiscent of the center of mass, except of being divided by the total mass. So it means that if you choose the origin of your reference frame as coinciding with the center of mass, the dipole term, the multipolar term in the case of mass instead of charge is 0. This is very, very important when you will be considering, for example, radiation due to the gravitational waves. You see that the first term is due to the quadrupole because there is no analogous. Instead, getting back to the electrical charges, here this guy, thanks to the fact that charges can be both positive and negative. For example, if you consider it as the simplest system, which is made of just two charges, you have two charges, but one is positive and the other is negative, you see that the first term is 0 because the total charge is 0, so you don't have this. So the first term is indeed a dipole moment because these two terms do not cancel out because they have opposite charges. You don't have an analogous case in the mass instead of charge because mass can only be positive. So there's a huge difference which has an impact when you in the multipolar expansion comparing the electric charge case versus the mass case. Anyway, this is just to let you know that, for example, when you consider a system which is electrically neutral, So the total charge is 0. You have as many electrons and as many ions. It means that the total charge is 0. So it means that in the multipolar expansion, the first term is not this guy. There's no, if the total charge is 0, you don't have this. The first term is the dipole moment. Okay, so getting back to our point. So let's go back. We just derived the resulting radiation field for a system of a charged particle. We saw that we can just, it depends just on the second time derivative of the newly defined dipole moment. So now we want to calculate the very same quantity that we calculate in the case of one single particle. So the power per unit solid angle. So I'm not going to repeat the same argument that I used in the case of one single particle. You see that the power per unit, P is the power here, so is dW over dt. So the power per unit solid angle is just, you get it just by multiplying S pointing vector time R squared. In this case, R0, because we just assume one single position for all the particles. So again, just if you just take the very same formula for Poynting's vector, this is Poynting's vector times R squared. Now let's replace E rad for the system of particles. I remind you, I rewrote here above to remind you. E rad, we just obtained n vector, double time derivative of the dipole moment, of the electric dipole moment. So in this case, again, a very similar equation. You gain a factor of sine theta in this due to this vector product, because theta is the angle between what? Pay attention. We don't have any more one single acceleration. What the role played by the acceleration is now played by the dipole moment, or not the dipole moment, by the double time derivative of the dipole moment. So vector d double dot. So sine theta is the angle between this vector, so the d double dot, and n. And the rest is just the same. Just the same. You just see that. Okay? So we recover, if you want, an even easier formula for the Larmor radiation in the case of a system of particles, in which you see 2/3 modulus of the second time derivative of the electric dipole moment squared over c cube. Of course, you can consider one system, the very special case of the system made by just one single particle. In that case, if you think d is just qr, so the double time derivative of d is just q times modulus of the acceleration of the particle. So you recover. So this is a generalization, because of course, in the end, one single particle is a very special system of particles. So this is generalizes. If you know that, of course, you automatically know the Larmor formula for one single particle. And okay, it's really, so what I started at, okay, so yes, I think we'll finish next time, because it's already, it takes a few slides. We will see then in the end also. So far we obtained the power by a system of particles still in the non-relativistic regime. I remind you, as a function of the second time derivative of the dipole moment. We'll see. We already saw the dependence. You see the very same dependence on direction. Again, sine squared. So the very same dependence. Of course, in this case, you have to pay attention to the direction. The angle is between the second time derivative of the dipole moment and the generic position, the generic direction. The next time, we will see how this power depends on frequency. So what is usually called as the spectrum. So how energy is emitted as a function of frequency. It takes a while because we have to go through Fourier transforms, but I let you find out next time. Any questions? Okay. So